Okay, let's talk a little bit about how to solve force problems. Solving force problems is actually really simple. We really just need a few tools in order to do it. Our first tool that we're going to need is called a free body diagram. So let's pretend there is a mass sitting on a desk. What a free body diagram does is it allows us to look at all of the forces with our eyes. I obviously can't see the forces that are there, but I know that if I'm on Earth, this mass is going to have a force of gravity downward on it, also known as its weight. And if it's sitting on the desk, it's going to have the force of the desk, which we have a tendency to call instead the normal force. Timeout. I got to take a timeout here. Everybody gets this wrong. Normal force doesn't point up. Normal force doesn't point opposite of the force due to gravity. The normal force has absolutely nothing to do with the direction up, and it has nothing to do with the force due to gravity. In fact, what normal means is perpendicular. So what makes this force normal is that it is perpendicular to the surface of contact. So a normal force is always perpendicular to the surfaces that are in contact with one another. In this case, that 90 degrees is between the mass and the desk. So let's make sure we understand that. Okay, so we're just going to go ahead and call this a normal force. We're going to understand that that force is coming from the desk. So there's our first tool. Our second tool is our eyes. We have the ability to look at something and see, one, if it's stationary, if it's at rest, two, if it's in motion, three, if it is changing its motion. Now, going back to Newton's laws, motion has nothing to do with whether or not there are forces on an object. But changing motion does have something to do with it. So we'll go over that again in a minute. We're going to use our eyes, or we're going to use what the problem tells us to determine, is the object changing its motion? What does that mean? That's a simple way of saying, is the object accelerating? What does it mean to accelerate? It means to speed up, slow down, or change direction. Speed up, slow down, or change direction. All three of those things are a type of acceleration. They're a way of changing our velocity. Remember that velocity is a vector quantity, it has a magnitude and a direction. So if I am speeding up or slowing down, I am changing my speed. That's the magnitude aspect of velocity. If I'm changing my direction, well, I'm changing my direction. So the vector points in a different direction, and all of those things are a type of acceleration. So that's another tool that we have. Is this object accelerating? The last tool, and I'm calling it a tool, that we really need is an understanding from Newton's laws and the meaning of some of the words that we're going to talk about in Newton's laws. Specifically, the law that says, and I'm going to write it this way on purpose, the law that says the following. This is Newton's second law. What does it say? It does not say, let's start with what it doesn't say. It does not say that a net force is necessary for motion. That is not what it says. It says a net force is necessary to cause an object or a mass to accelerate or change its motion. So when a net force is present on an object, that object will change its motion. That's the meaning of this equation. There is an equivalence between how much extra force there is, extra meaning non-zero, anything that's more than zero. There is a relationship between how much extra, how much more than zero force there is, and how much something will accelerate times its mass. The only other thing that I need to solve a problem is to understand that F net means adding all the forces. If I understand that, I can solve any force problem no matter how many forces there are and no matter what is going on. Those are the tools we need. Let's put this into practice. I'm going to show a simple example and then I'm going to show a little bit of a more complicated example. Let's say I have a mass, and let's say that mass is, let's use some nice numbers, 2 kilograms. And let's say there are two forces on the object. And force 1 is 10 newtons, and force 2 is 4 newtons. Now, we can see from my free body diagram a couple of things. One, all of these forces are acting along the same axis. That's important. And two, these forces have a direction. Force 1 is to the right and force 2 is to the left. It is up to me then, when I am solving this or when I'm writing this stuff down, to choose a direction that is positive. So let's go through this problem. I've drawn my free body diagram. All of this is along the same axis, so I'm good. Maybe I will put down the axes. Let's pretend there's a y-axis and an x-axis. Let's decide that this direction is the positive x-axis and this direction is the positive y-axis. It's completely up to you, but that's what I'm going to do. That means if to the right I've called positive, this is a positive 10 and this is a negative 4. Great. Step 1 is done. I've drawn my picture. I've now identified the forces that are there. And maybe the question is, what is the acceleration of this object? This is the simplest type of question I could probably get. So I need to write down two things. F net equals ma, and F net equals all the forces. You will notice I did not say F1 minus F2. That is because when I plug the numbers in, I will put the signs on them. I will then see if there's anything I can solve for. I don't yet know F net, that's an unknown. I do know my mass, and I don't know my acceleration. So this equation is not solvable. Okay, I don't know F net, but I do know these other two things. So now I have a solvable equation. F net equals 10 newtons plus a negative 4 newtons. F net is 6 newtons. Now that I know F net, I can go back and solve MA. So now I know that MA is 6 newtons. So 2 kilograms times A is 6 newtons. And that means that my acceleration is, let's divide, 6 divided by 2 is 3. Yes, you could say Newton per kilogram, but we're going to write meters per second squared. And look at this. All of these things were positive. This is positive. The right is positive. Hey, look at that. That makes sense. My F1, my force to the right, was larger than my force to the left, so my object will accelerate or change its motion to the right. Does this mean the object is moving to the right? No, it doesn't. This doesn't tell us anything about which way the object is moving. I don't know how fast it's moving. All I know is that it's accelerating to the right. It could be moving right now with a velocity to the left of 100 meters per second. And after 1 second, it'll be moving at 97 meters per second. And after 2 seconds, 94 meters per second. Because the acceleration is opposite the velocity. So the sum of the forces, all this information does not tell me what direction an object is moving. Is this object moving up and down? I don't know, maybe. I couldn't tell you. All I can tell you is that it's not accelerating up and down because there are no forces in the up and down direction. So we need to be very, very careful about how we interpret this information. A net force can only tell you about something's acceleration, not about how it is currently moving. That is the simplest example that I can give. Let's go a little bit more complicated and let's just move a little bit at a time. Maybe this time I'm given an object and I'm told F2 is 5 newtons, F1 is unknown, and the acceleration of the object is to the right, and it is 4 meters per second. Okay, now in this problem, I'm not actually told if F1 is to the left or to the right. I'm just told that there are two forces, F1 and F2. F2 is to the right, the acceleration is to the right, and my mass is 3 kilograms. And the question now, again, what is F1? So, again, maybe we should just get in the habit of doing this every time. I'm going to make two axes. I don't have to call them X and Y. I don't have to make X horizontal and Y vertical, or however you want to imagine this picture is. But that's what I'm going to do here. All of these forces are along the same axis, so I can add them together. And I'm going to write down my equation that says F net equals MA, and that says F net is equal to all the forces, which is F1 plus F2. Now, I drew F1 to the left and F2 to the right because it made for a nice picture. Again, let's say I don't know what direction that F1 force was. Just for giggles, let's call to the right negative. And let's do this step right now where I'm going to transfer this to now say MA equals F1 plus F2. And let's solve. Okay, my mass is 3 kilograms. My acceleration. Well, I decided the right is negative, and since the acceleration is to the right, negative 4 meters per second squared equals F1. I don't know. I don't know what F1 is right now, so I'm just going to write equals F1 plus F2 is 5 newtons. It is to the right. I am certain of that. So negative 5 newtons. Negative 12 newtons equals F1 minus 5 newtons. Negative 7 newtons equals F1. Oh, this gave me a lot of information. Not only did it tell me that F1 has a magnitude of 7 newtons, it told me that it's negative, meaning I drew it wrong when I first drew my picture. F1 must also be to the right. And again, in my picture up top, I didn't include positive or negatives because I drew arrows instead to tell me what direction these things were acting. I want to quickly touch on something before we finish up here. And I'm going to make some more videos with more complicated problems, especially ones that involve two objects that are connected together via some sort of rope, maybe a pulley system. But before I do that, I want to talk about the fact that I've been drawing these axes as I've been doing my problems. This is really important because if you get problems that have forces along two different axes, you have to do this process more than once. You are going to have to talk about your x and your y axis independently of one another. You will have to do this for both axes. The net force total on the whole thing will be the two forces combined, but we can't simply add x stuff and y stuff. We should be familiar with the idea that we need to use maybe the Pythagorean theorem or sine, cosine, tangent. That's something that will be talked about somewhere else. But just know that if I have forces in my y direction and forces in my x direction, or rather I should say if I have forces that are 90 degrees to one another, that's a 90-degree angle, they do not belong in an equation together to solve here. There are certain times we can figure out if there is a relationship between them, if friction is involved, but I have to do this process separately. Meaning, if I called this F1, F2, F3, F4, then in the x direction, I would have F1 plus F2, and in the y direction, I would have F3 plus F4. So again, if you get a problem like this, we can't simply put all of these together. I cannot do F3 plus F4 plus F1 plus F2. I cannot do that. They do not belong together because they are 90 degrees together, and I can't do normal algebra with them. I can't do normal addition and subtraction. So if you see that, then it's time to watch another video about how to deal with when forces are along multiple directions that are not along the same axis.